Welcome back to astronomy. So today we're going to be looking at a little bit more to do with light, following up from where we left it before. And that'll actually take us to talking about some really big stuff like the expansion of the universe and ultimately the Big Bang itself. So just to recap a little bit from last week, we talked about the electromagnetic spectrum. And the electromagnetic spectrum includes what we call visible light, but there are many types of light that are not visible to us. They're all electromagnetic radiation types. The only real difference is their size. So when you think about light, for this course, we're going to be thinking about the whole thing, from radio waves, a really big wavelength type of EM radiation, to microwaves, infrared, through visible UV, X-ray, gamma rays. So generally speaking, we talk about the shorter wavelength, higher temperature, and higher energy type of light, because something that's really hot gives off blue, right? So that's higher energy, and it also represents material that's higher temperature, would be bluer, or putting out bluer light. Redder light is generally going to be coming from lower temperature things. That's longer wavelength, closer to the infrared and then radio. And that's longer wavelength and lower energy, lower frequency, right? So all these things relate. Energy is directly related to frequency, and frequency times wavelength gives you the speed. Since light with a big frequency has a small wavelength, and light with a small frequency has a big wavelength, it ends up being that when you multiply frequency and wavelength, you get one number for all types of light, and that is the speed of light. And that is a constant of nature, and a very important one. So that's a very important equation for us. All right, speed equals frequency times wavelength. Now, when you have a hot object, it puts out what's called a black body curve of radiation. So on the y-axis of the graph, we have intensity, and then on the x-axis, we have wavelength. And intensity versus wavelength is telling us how bright the object is at different wavelengths. And what you can see is that for all hot objects, the intensity rises as you go to bigger wavelength, and then it reaches a peak at some particular wavelength. Down here, you can read the wavelength off. Reaches a peak at some particular wavelength, and then it starts to decrease. That peak wavelength tells us the temperature of the object. All right, so if you'll remember, there are two keys to blackbody radiation. One is that, assuming all these things are the same size, one is that the hotter object will put out more light at all wavelengths. Right, at all wavelengths, the 12,000 Kelvin curve is higher at any particular wavelength than the 6,000 Kelvin curve. And the 6,000 Kelvin curve is higher at any individual wavelength than the 3,000 Kelvin curve. But notice that the peak for the hotter object, peak moves to lower wavelength, which is higher frequency and higher energy. So a hotter object is putting out higher energy light overall. A cool object may peak in the infrared. You do, after all, you put out radiation in the infrared. Whereas an extremely hot object can peak in the UV, a much lower wavelength type of light, but higher energy, right? So these two things are directly related. The temperature of an object in Kelvin is going to be equal to 0.0029 divided by whatever the peak wavelength is in meters. Now, I noticed as we were doing the homework assignment in the last lesson that some people had trouble getting the units right. That is not an overly hard thing, but it does take practice. You got to be familiar with your calculator, and you got to be familiar with scientific notation. So make sure that you're confident with that, because you should be getting it right easily for the test if you've practiced. Now, what we're going to look at today is spectra, is the light that we get from different things. And it can tell us a lot more than just temperature. Temperature is a very useful thing to know for something like a star or a planet or whatever. Temperature is very useful to know, but there's a lot more that we can get out of light. So what we're going to talk about for the first half sort of this lesson is how much we can get out of light. And for the second half, we're going to be talking about a particular example of that. When we studied the light from galaxies, we ended up learning all about the Big Bang. So a spectrum is the wavelengths of something that are being put out. So the amount of energy being put out at different wavelengths from an object, all right? And this has to do with what an object is absorbing, but also what it is emitting. Emitting is to put something out, right? A light bulb emits light. So there are, broadly speaking, two kinds of spectrum. If you look straight at a light bulb and you pass that white light through a prism, you will see that that white light is actually a whole spectrum of light, all the colors of the rainbow and more. And it is continuous. You've got red, you've got orange, you've got yellow, you've got green. It is continuous. So it's called a continuous spectrum or a continuum spectrum. On the other hand, if there's something between you and that light bulb, gas, cold gas can absorb certain colors. And so when you put that light, or when you, let's say we got a light bulb and then cold gas, the light goes through the cold gas, then through a prism, and then to your eye, or to the wall, or whatever, the projector screen, or to a camera. Anyway, the important point is that when the light finally arrives, the cold gas has absorbed certain colors. There's colors missing. We call this an absorption line spectrum. There is also a third type of spectrum called an emission spectrum, but we're not really going to talk about it. All right, that's if you're just looking straight at a cold gas with nothing else there, then all you're going to get is a few certain colors and nothing else. So it's kind of the opposite of the absorption line spectrum. But we're not really going to need that as much as we need the absorption line spectrum. So a continuous spectrum, again, you've got a black body emitter, and you pass its light through a prism, and you get a continuous spectrum. You just get all the colors more or less continuously, but not equally, all right? So if you have a very hot or dense object that is hot, then it will put out all colors with no colors being blocked or lost. So this is basically perfect black body radiation. But remember, it's not all equal in amounts. So if I show you the picture, this rainbow that's coming out, that's not really telling you how much light is being put out at different colors. So if we really want to see a better comparison, the graph tells us a lot more information, right? The graph tells us that the 15,000 Kelvin star, for example, the blue line, is putting out way more energy at 100 nanometers than it is at 10,000 nanometers, right? So it tells you the variation in the amount of energy at different wavelengths, the amount of energy output. And the 15,000 Kelvin star, it's putting out the most light at about 100 nanometers in the UV. But we've already talked about these. These are the black body emitters that we talked about more last class and already sort of recapped today. So let's continue. Right? So an ideal black body object, and most things, of course, are not truly ideal, but an ideal black body object will absorb everything that hits it, and it'll put out a perfect continuous spectrum. That means it's putting out all colors, not necessarily at equal amounts, but it is putting out all colors over a certain range of wavelengths. There will be some things like, for example, our sun just does not put out radio, for example. There's just basically zero, right? It peaks in the visible light and it produces less and less and less and less as you go to bigger wavelengths. But so it's not equal at all wavelengths, but it is putting out a continuous across that range. It is putting out all colors of light, right? So stars are examples of that. Light bulbs, which are just hot metals, right? It's a hot strip of metal potentially, or a hot, yeah, we'll just stick with light bulbs like that, and it's a hot strip of metal, and so it is a hot dense object, right? So those are pretty good as ideal black body objects. So we've already seen this. You can display a spectrum in two different ways. If you project the light onto the wall, then you get a continuous spectrum that looks like a rainbow. And so this is very obviously a continuous spectrum to our eyes. But this is equally well a continuous spectrum. It just gives us a lot more information. And it very nicely and conveniently, it gives us information beyond the visible spectrum. How am I supposed to show you the rainbow continuing into the UV or into the infrared? But in this graph, it doesn't make a difference. In fact, I have to show you which part the visible actually is. So this graph does a better job of showing you the whole range, right? Without worrying about the fact that we don't have colors in our heads for UV and infrared variations, right? Here, it's just by wavelength. And that's all colors really are, it's different wavelengths anyway. An absorption spectrum is very important for astronomy because most things are not perfect black bodies. There's not a lot of perfect things in nature. So if you have a black body and then between you and it, there is a cool gas. So the light passes through the cool gas and then you put it through a prism and the prism splits it by wavelength onto the wall, and then painted on the wall what you see is a rainbow, but some colors are missing. They've been absorbed by the cool gas. Hence it is an absorption line spectrum, right? And we call it a line. Each of these is called a line for kind of obvious reasons, right? It is a missing line in the spectrum. So if light with a continuous spectrum shines through a cloud of cooler gas, the gas can actually absorb individual particles of light that are called photons. Light is a wave, but light has an important property. It's called wave-particle duality, and this has to do with quantum mechanics, and it gets weird. But the important point is you can talk about light as a wave. You can also talk about light as a whole lot of particles, and that actually works both ways. Particles, just like, you know, bouncy balls or whatever, or paintballs. You can talk about it that way. And so cool gas, the atoms in the gas will actually absorb individual photons, particles of light, as they pass through the gas at specific wavelengths, giving rise to our absorption line spectrum. So if we look at that as a rainbow, you can see how certain colors are missing. What does that look like on the graph? Right? On the graph, we're going to take the continuous spectrum, but then we've got to have less light at specific wavelengths. Not necessarily zero light, as you can see. So instead, on the graph, we see the same continuous spectrum that we normally would, but where there's a black line, there is a dip, right? There's less light at that particular wavelength. And so there's a dip in the spectrum right there. These are absorption lines in our spectrum graph versus absorption lines in the spectrum rainbow. And they're equally visible in both. So the dark line, right, or the missing color, or dark line spectrum, or absorption spectrum, in the graph, notice, and they really are the same, of course. They are this is the same thing, right? Is here we've projected it on the wall, here we've actually measured it as a graph. And you can see it doesn't go all the way to zero. If it were truly black in this line, and there was zero intensity at that particular color, then it would go all the way to zero, but it doesn't have to be truly black. It's just darker than the rest, okay? Almost no light at that particular color, but not necessarily no light. So anyway, particular colors are missing to some extent, but only those particular colors, all right? So this normally happens. You will, in nature, never really get a perfect blackbody spectrum. There will always be some sort of cooler gas between you and the thing you're observing. If you are observing from the ground out into space, for example, we have an atmosphere around the Earth. We are in the atmosphere. So the atmosphere is between us and the thing we're looking at in space. And the atmosphere will absorb certain colors. We know what colors it absorbs, so we can identify its effect. But nonetheless, the atmosphere will always have this impact. Even the sun, if we look at the sun is not actually a solid ball, is it? The sun has a thin, tenuous atmosphere called the corona. Not the coronavirus, just the corona. The sun has a thin, tenuous atmosphere around it, which is parts of it are cooler than the sun itself. And so as the sun's light passes out through its own atmosphere, certain colors are just reabsorbed right away. And so the sun actually emits, it actually emits an absorption line spectrum. So you can't get away from this. There is no true continuous spectrum from normal objects. Normally, there's some absorption lines in it, right? Cooler gas will always be there, and it'll always absorb some particular colors, creating absorption lines at the wavelengths of whatever it emits or whatever it absorbs. So if we look at the sun, for example, the sun is producing its light in its core, which is a 15 million degree core. But then the core, that light has to pass through quite a lot more sun before eventually it makes it out to us. And the temperature of the sun varies all the way from the core to its outskirts. So the outermost layers of the sun, and it's still fairly dense at the outermost layers, the corona extends out even beyond this, and it gets potentially parts of it are cooler. But even so, the outer layer of the sun is about 5,800 Kelvin, just under 6,000 Kelvin. And that's substantially cooler than the core. So whatever light is emitted in the core, parts of that light will be absorbed by the atoms in the rest of the sun, before that light even escapes the sun and comes on its journey to us, 8 light minutes away. So light made in the star has to pass through the rest of the star and then its outermost atmosphere and then our atmosphere before finally reaching us on the ground. All right, so some light gets absorbed while passing through the sun's atmosphere. That's inevitable. And it turns out different atoms will absorb different colors. And you know what? We know exactly what colors they'll absorb. In fact, this is how we identify elements. Is you can look at the absorption lines that are present and say, oh, there is some hydrogen gas in there, because I know exactly what colors hydrogen likes to absorb. It's a fingerprint. All right, it doesn't just absorb one or two, it absorbs potentially hundreds of different colors all through the spectrum, and you can identify them. All right, so we can identify what things are made of, and this is an incredibly useful tool. Think about it. We don't have to go out to the sun, stick a finger in, and then lick the finger and be like, tastes like vanilla. No, we can just look at the sun, we can see what spectral lines are in the spectrum, and I can tell you exactly what elements are in the star. Atom by atom. That is incredibly useful. In fact, element 2, helium, right? This is the periodic table, in case you've never seen it before. This is the periodic table. Element 1 has 1 proton, that's hydrogen. Element 2 has 2 protons, that's helium. Element 3 has 3 protons, that's lithium. Beryllium, boron, carbon. It's just a proton number list. Element 2, helium, we actually identified it by its spectral lines in the spectrum of the sun before we ever found it on Earth. That's why it's called helium. Helios was the Greek god of the sun. So we actually discovered helium in the spectrum of the sun because helium makes up some 28% of the sun. We discovered it in the sun before we ever found it on Earth, which I think is pretty crazy. That's why it's called helium. Anyway, so we can do this for the sun. We can do this for the atmosphere of planets in our solar system. We can do it for other stars, galaxies, nebula in space, distant quasars. We can do it for basically anything that we're looking at that's made of atoms. Is we can tell exactly what atoms are in there, which is an incredibly useful tool. We can identify composition without having to visit. And for distant stars, which we will never visit, at least in our lifetimes, that's an incredibly useful tool. All right. So here's some examples. These are the specific colors that are missing based on the presence of, so hydrogen absorbs these colors in the visible light. Helium absorbs different colors. So if you see this color of red, that color of orange, that color of green, and that color of indigo, you know there's helium in the gas. Sodium absorbs these 2 colors in particular in the visible spectrum and not much else. Calcium absorbs different colors. To different extents, by the way. Notice that this line is much darker than this line, right? So these characteristics are standard. You can get this in a lab. You can just make a bottle of hydrogen gas, put it between you and a light bulb, and see what colors it absorbs. And indeed, in basic physics labs, people do this, right? This is an easy experiment to do. You can see what colors hydrogen absorbs, and then you can look out to space and you could look at a distant star and you can say, hey, look, those same things are missing there. And so you can identify what things are made of in space. That is how we do astronomy. All right, we are not just taking pictures. I said this last class, we're taking spectra. And when you take a spectrum, you can identify temperature based on peak, and you can even identify composition based on the lines, which is incredibly useful. One of the other great things that we can identify is motion. And this is surprising, but very, very useful. Have you ever heard of the Doppler effect? Have you ever heard a fire truck driving down the street sound oddly different when it's coming closer to you versus when it's moving away from you? So this is the Doppler effect. The Doppler effect is that there's a change in wavelength of sound or light or any wave when the source of the wave is coming towards you or away from you along the line of sight. All right. So if a fire truck is coming towards you, notice what happens. this thing is moving to the left. So if you're standing over here, it's coming towards you, it's emitting a wave, a sound wave. The wave gets compacted ahead of it. Higher frequency, higher pitch. A fire truck coming towards you sounds like wee 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 wee. I do a great fire truck, I know, thank you. Thank you very much. Whereas if you're standing over here and the fire truck is driving away from you, the wavelength gets bigger, more spread out, and the pitch drops. The frequency drops. And so now the fire truck sounds like wee, wee, wee. Do you want me to keep going with it? So anyway, you can tell, and this is an audible difference, all right, that you can tell. So if something is coming towards you with some speed, then what happens is as it approaches you, it's putting out a wave ahead of it, right? It's putting out a wave. It puts out waves in all directions. So if you've got a parked fire truck, it sounds the same in all directions. It's putting out waves to the left, to the right, all around it. It's putting out waves. But now if it's moving towards the wave it just emitted, right? So it just spat this wave out, and now it's coming closer. And by the time it sends the next wave out, right, it's not as far. It has compacted the waves ahead of it because it's kind of catching up to the waves that it previously emitted. And so ahead of it, the waves get compacted. The wavelength is decreasing. That means we know when wavelength drops, frequency goes up, pitch goes up. And that happens for sound, right? You've got a fire truck, the pitch goes up, but the same thing happens for light, that the frequency goes up, all right? So if you hear a siren, this is a great quality pixel animation that someone made, or not even an animation. Look at this, how many pixels are, anyway, whatever. If you hear a siren coming towards you, right? I hope he's not driving straight at you. Get out of the way, you fool. The wavelengths are compacted because it's emitting a wave and then catching up to the wave it just emitted before spitting out the next one. And so it's small wavelength, high frequency, high pitch. Whereas back here, this gorgeous looking lady over here, who doesn't have a nose, but that's okay. The way here now, the siren is putting out a wave backwards, but then it keeps driving forwards. And so by the time it spits out its next wave, so it put out this wave, and then by the time it spit out its next wave, it was actually further to the right. And so this wave is now further to the right than it otherwise would be. So the wavelength behind the car has been, and there's a missing wave over here, by the way. They should be evenly spaced. Anyway, this really is a crappy picture. The wavelength back here behind the car is longer, bigger wavelength, lower frequency, low pitch. So if you hear a police car or a siren or whatever coming towards you, you hear high pitch, and then when it passes you, it becomes, as it's driving away now along your line of sight, as it's driving away now, you hear low pitch. That will not change with distance. This is not about distance. This is about a simple yes, no. Is it coming towards you? Yes or no. Is it moving away from you? Yes or no. Okay? Simple, is it coming towards you or away from you? It's not about distance. Volume, the volume of the sound will change with distance, how loud it is. This isn't about loud. This is about pitch. Okay, so if it's coming towards you, I don't care what distance it is. This doesn't tell us anything about distance. The car could be a block away. It could be a province away. It doesn't matter. Ignore the volume. You will hear, if it's coming towards you, high pitch. So let's pretend it's coming towards you. The volume will rise, sure, but the high pitch is not going to change. Okay, high pitch if it's coming towards you. That sounds terrible. Anyway, I really hope you enjoy my siren. Okay, so high pitch is if it's coming towards you, low pitch if it's moving away. And again, has nothing to do with distance, just is it coming towards you or moving away from you? All right, Doppler effect will tell us if it's coming towards you or moving away from you. So here's some real life examples. Obviously, an emergency vehicle, you can hear it. You can tell. Or a train running along the rails, you can hear the, chugga chugga. Or car or whatever. Doppler is obviously used for Doppler radar. This is how we measure the speeds of clouds and stuff. It's used for radar. It's used for, well, anything with radar, okay? So this is how we measure the speeds of things. When a police officer measures the speed of your vehicle and gives you a ticket, because what were you doing at that speed in that zone, man? What were you thinking? Anyway, what they've done, a radar gun, is exactly measuring the Doppler effect, all right? It's bouncing waves off you. It's emitting radio waves, bouncing those, or light waves, it doesn't really matter. It's bouncing waves off you, and that makes you a source for waves coming back towards their gun, radar gun, and that'll pick up the Doppler effect on the waves, and that tells you the speed, right? If you're parked, there's obviously no Doppler effect. So if there is substantial Doppler effect, then you must be moving fast. If there is an extremely substantial Doppler effect, you must be moving very fast, all right? So the amount of compression or expansion of the waves will relate to the speed, and that's what a radar gun will detect. Again, it's not about distance. It won't change as you get closer or farther. The question is simply how fast are you going, all right? So for light, if something is moving away from you, this will happen as well. If something is moving away from you, then its wavelengths will be stretched. Okay, everything it's moving away from will be getting more stretched out light. We call that a red shift because it is shifted to the red side of the spectrum. The red side of the visible light spectrum is the longer wavelength side, so we call that a red shift. Now please note, this doesn't mean it'll be red. You could have something that emits purple, and because it's moving away from you, it's actually going to look blue. That is a red shift because it is shifted to the red side. Doesn't mean it's shifted to the point that it actually looks red. It's just shifted to the red side of the spectrum. All right, so we call it a red shift. Might be a bad name because it sounds like it makes it look red. It makes it look redder. And it's weird to say that blue is redder than purple, but I guess it's true, right? Blue shift, on the other hand, is if something is coming towards you, then just like a fire truck would be high pitch, high frequency, if something is coming towards you, its wavelengths get compressed. And please do, by the way, you don't have to memorize this stuff, right? What I want you to do is try and remember this picture. That ahead of the wave emitter, the waves are compacted, smaller wavelength, higher frequency, and behind they're stretched. So try to remember that picture. So ahead of something that's emitting light, its wavelengths will get compacted. It'll be higher frequency, and the higher frequency side we generally call blue, even though I suppose it's purple, so again, not a great name, but we call it a blue shift. You could have something that is emitting infrared, but because it's moving towards you really fast, it ends up looking red. We would still call that a blue shift because it is shifted to the blue side of the spectrum. Okay, whether or not it's blue, it's shifted to the blue. Again, maybe not a great name. Maybe we should call it a right shift, but that's not quite as evocative, is it? Doesn't sound as good. So red shift, blue shift is what we've got, all right? So in astronomy, this is an incredibly useful tool because, again, we can pick up the motions of things, at least towards and away from us, the motions of stars, the motions of galaxies, planets, whatever. We can pick it up based on the light that they're emitting. Right? So if something is moving to the left here, it's getting closer to this lady. So she sees it blue shifted, not necessarily blue, but bluer. Whereas this guy sees it red shifted, redder than it otherwise would be. All right. So that's the potential of the Doppler effect. If something is stationary, then fine. If it's moving away from you, its light will be stretched out and redder, red shifted. If it's moving towards you, its light will be compacted, more blue, blue shifted. All right. That's the Doppler effect. Now, the truth is, though, that you will never see this. You can hear it for a siren because sound is a little bit more sensitive because the speed of sound is a lot lower. It depends how fast you're moving compared to the speed of the wave. The speed of sound is fairly low, so a fire truck is moving at some decent percentage of the speed of sound. Not a great percentage, but it's not zero either. The speed of light, on the other hand, it's pretty hard to move at even a remotely decent percentage of the speed of light. So overall, things won't really change their colors. I don't care how fast you run with a flashlight. The flashlight will not change color to the perspective of the person you're shining it on. All right. So overall, colors do not normally change, not very much at all. And keep in mind, the thing actually has to be moving towards or away from you, right? It's along the line of sight. So if the thing is moving to the left or right, then this person will notice a Doppler effect, potentially. But if it's moving on this screen up or down, is it moving towards or away from this person? No, not at all. So if something is moving perpendicular to our line of sight, there's no Doppler effect at all. And we'll never know that it's not parked. All right? So when an object is moving perpendicular to your line of sight, you will not detect a Doppler effect at all. And you can draw the wrong conclusion from this. You could say, oh, I guess it's not moving. And you're wrong. So keep in mind the Doppler effect. It's only telling you about the part of the motion that is towards or away from you. Something could be moving diagonally. Some of its motion is towards you, some of its motion is not. So you're only going to pick up part of its motion. All right. And so what you're seeing, what you're not, gets a little bit more complicated. All right. Now, keep in mind the light that something is putting out. There's more than just white and black, right? It's more than just on or off. There is a lot of information on light. So if you have a hot light or a hot light source and the light is passing through a gas, we put it through a prism and then we get a rainbow out and we see those missing colors, those absorption lines. Keep in mind that's almost always going to be there from any light source. All right, when a hot object's continuous spectrum is passing through a cooler gas, and that's almost inevitable. Right? So in astronomy, when we look at the light from something, we've got these absorption lines. And you know what? The overall color of a star may not change very much if it's moving a little bit away or a little bit towards us. But those lines in the spectrum are sharp and clear as day. And they will shift. And when they shift, even by a little bit, you can pick that up. So that's how we actually do the Doppler effect measurements that we do in astronomy. And it's not even a hard calculation. That's how we do it. We do not just look at a star and say, is it red? Because that would tell us nothing. Because again, overall color will not change. All right. A red star is looking red because it's cool. A blue star is looking blue because it's hot. Overall color will not change unless the star is moving at basically the speed of light, which does not happen. All right, so overall color does not change. But if we look at the spectrum of the star, we know where those hydrogen lines should be. And hydrogen makes up 70% of most stars. So we know where those hydrogen lines should be. We know exactly what wavelength those hydrogen lines should be at. And when we look at the spectrum and we discover they're not in the right place, all the lines, the fingerprint is shifted to the red. It is a red shift. That star is moving away from us. Or on the other hand, we look at a star and all these absorption lines are actually shifted to the blue side, right? Like look at this line over here. It's shifted to the left, to the blue side. This line shifted to the blue. All of them are shifted to the blue side, right? This one, for some reason, there's a little bit of green in there. That's just a pixel effect, low pixelation. They're the same lines. These lines, they're all shifted. They're supposed to be here. They're all shifted to the red side. These lines, they're all supposed to be a little bit further over to the right, but they've been shifted to the left. They've been shifted to the blue. So this star is moving towards us. This star is moving away from us. And it doesn't have to be by very much for this to be noticeable. So let's try this one. And this is a black and white picture. Who cares? The blue side is the left. The red side is the right. So for these three spectra, one of them is not moving, okay? One is moving towards you, and one is moving away from you. Which is the one moving towards you? It does make it a little bit more complicated, the fact that you don't know which one is motionless. So what are the normal lines? But I'll tell you this much. The one that's moving towards you has to be blue shifted. So which lines are the most to the left? And the answer is C. All right, these lines are the most to the left. I've told you that one of these stars is motionless and one of these stars is moving towards and one is moving away. So if this is the blue shifted one, this is the one moving towards you, which must be the motionless one and which must be the one that's moving away from you? The most red shifted lines, without even knowing which one is necessarily motionless, these are the most red shifted. These are the lines that are most to the red. All of these have been shifted to the right. So this must be the star moving away from you, and this one must be the motionless star. All right, so these are the normal lines. If we grab them all and shift them all to the left, that's a blue shift. It's coming towards you. If we grab them all and shift them all to the right, that's the red shift. That's the one moving away from you. All right, so you can identify it by eye. And early astronomers did this stuff by eye. They were very good at identifying this stuff. These days we can do it with a computer. All right, so that's the one moving towards you. So what can we actually learn by looking at a star's light? We don't just take pictures, right? We take a spectrum and we can get temperature. But based purely on the peak of the curve, right? We can get what the star is made of, which is an incredibly useful tool based on the absorption lines. And that tells us exactly what atoms are in the star. And we can even figure out the star's motion, or at least the part of the motion that is towards or away from us, which is the Doppler shift. All right, so there's a lot of information that we can get out of light. So now let's take a look at an example of how we can use our understanding of light to understand something really big like the universe. So cosmology is the study of the cosmos overall, the universe. And there's quite a lot we know about our universe. As big as it is, we can figure a lot of it out because the rules that govern our universe are the same rules that apply everywhere. So when we say the universe, that means literally everything, right? So the universe is the word for everything. That includes obviously our solar system and all the stars and all the galaxies and all the groups of galaxies and all the clusters and superclusters and everything. All right, that's the universe. And cosmology is the study of that. So everything we know about the universe in particular relies on one thing, the cosmological principle. And the cosmological principle is basically the idea that our universe is in fact understandable. And there's simply just two things that we need to rely on for that to be true. All right, so the cosmological principle has two parts. One is that the universe must look the same in every direction, more or less. Not exactly. Obviously, when you look to your left and when you look to your right, you see different things. But overall, the universe, if we point our telescope one way, should look roughly the same as the universe if we point our telescope a completely opposite way. All right? The word for that is isotropic. In all directions, it must be the same. That's what iso means. All right? It must be the same in every direction, basically. All right? Again, so here we see the Hubble picture of extremely distant things. A deep field is when you simply point the telescope at nothing and you leave the shutter open for as long as you can. And so these are very deep fields. They're showing us the farthest things that you can see. And every dot in these pictures is a galaxy. Every single dot in these pictures, from the big ones to the teeny little dots that you can barely see, is a galaxy, each containing hundreds of billions of stars and who knows how many planets. So these are very distant, right, views of our universe. And what you can see is that they both look basically the same, right? It's not like over here we see all blue galaxies and over here we see all red galaxies. It's not like there's way more galaxies over here than over here. In both directions, opposite directions, they look pretty much the same, right? Which is isotropic. So when we look 12 billion light years away into different directions, they look basically the same, right? On average. They're not the same picture, obviously, but on average, the qualities are the same in both directions, right? So isotropic, and the universe must also be homogeneous. That's part two. Okay, homogeneous means uniform in space. So they have the same qualities in space as far as we can see. All right. So in other words, if you went very far away in a spaceship, you would find yourself in a space that looks pretty much the same as it does here. Not identical, again, okay? This doesn't mean that there's a clone of you living on a planet that's identical to the Earth, you know, a billion light years away, obviously. What this means is that, again, overall, on average, two different places will be basically the same, all right? Two widely separated places in the universe will be basically the same. Now, again, over small distances, this is obviously not the case. One star is very different from another star. One galaxy is very different from another galaxy. But over very large distances, the spacing between galaxies will be on average the same. The qualities of the stars that you find, the compositions of the galaxies will be basically the same, right? That sort of overall qualities will be the same from place to place. This is fundamentally important because if you think about it, everything that we understand about our environment is based on the rules of physics, biology, chemistry, the laws that science has taught us about. And if our location in the universe was completely different than some other location in the universe, that would be because the other location of the universe has to have different laws of science, different laws of physics, different fundamental laws governing its behavior. And if that were the case, how could we possibly understand it without flying all the way out there and doing our science experiments all over again and trying to understand the new sciences that govern that location? We would be doomed to never understand those other places because they would have different laws. But if everywhere in the universe is basically on average the same, then that means the laws that govern here govern there. And so we can understand there just as well as we can understand here. And now we can understand the whole universe at the same time. All right. So let me give you some examples. So picture A here, this is homogeneous and isotropic. So for observer 1, everywhere you look, in all directions, the spacing of things is basically the same, the density of things is basically the same, and if you even move to a different location, things still look the same. All right. So everywhere you look and everywhere you are is basically the same. In situation B to the right, it is not the same. For observer 1, if you look to the left, you see dense stars or dense galaxies. And if you look to the right, you see very little. You see emptiness. That is not isotropic. Two different views, two opposite things that you're seeing. And similarly, unsurprisingly, if you are on the edge of things in situation 1 versus in the middle of the dense things in situation 2, this observer is in a place where the laws of science must be different. And so observer 1 would have a very hard time trying to understand the environment of observer 2. So this is not homogeneous, very different locations, and very different views. Here we see homogeneous but not isotropic. Homogeneous means, again, that in two different locations, things are basically the same. So here what we've got is stars laid out in sort of parallel lines, or galaxies laid out in parallel lines. And there's gaps between the parallel, right? Between the parallel lines of galaxies. So it's a little bit like they're laid out on the lines of a lined piece of paper, right? And there's nothing between them. Well, in that case, observer 1 and observer 2 are basically experiencing the same thing. They look around and they see gaps, right? So it is homogeneous. There's a pattern, a strange pattern. And so for observer 1, if you look along the line versus perpendicular to the line, you see something very different. You can see gaps if you look this way, and you see no gaps if you look this way. So it's not isotropic. All right. Similarly, here we have a situation where everything is moving, but only up or down in the picture, not side to side, not diagonal, just up or down in the picture. So if you look up or down in the picture, you see things moving that way. If you look side to side, you see nothing moving that way. No Doppler effect would be detected side to side. And so this is not isotropic, but it is homogeneous. Right? So anyway, if we really want to understand the universe, then it needs to be homogeneous and isotropic. It needs to be the same in every direction. Even if we were to be in a different place, it would be the same. And that way we can apply the rules of science to all of it all at once. And everything we know about the universe, that is the case. It is homogeneous and it is isotropic, and so it is understandable. All right? So that's the implication of the cosmological principle. All right? What this means is First off, the universe can have no center. It can't have a center, because if it had a center, there would be a very different view from the center than anywhere else. All right? Are we the center of the universe? I mean, of course, I am the center of the universe. Are we the center of the universe? Come on. The process of science over the last hundreds of years have taught us that we are not the center of the solar system. We are not the center of the galaxy. We are not the center of things. All right? So get over yourselves. We are not the center of things, okay? The universe can have no center. What would be there? A rainbow in a pot of gold. No, it doesn't make sense. The universe cannot have a center, all right? So that's the first implication. The second implication is it can't have an edge. Because if you were over the edge, you would obviously experience something very different. The universe would not be isotropic, or sorry, it would not be homogeneous if it had an edge, right? You would have two different experiences in two different locations there. So it can have no edge and no center. This means that one solution to this is that it is infinite. It's actually not the only solution, but if it's infinite, which we think it probably is, then there's no center and no edge. All right. So returning to the Doppler effect, okay? The Doppler effect is what we used to figure out the true nature of our universe. If something is still, then it has normal lighting, right? And the spectrum will show hydrogen lines and helium lines and all the other lines of atoms in their normal locations. If something is moving away from you, those lines will be red shifted. If something's moving towards you, those lines will be blue shifted. And you can measure that very easily. So this is what Edwin Hubble used to study distant galaxies in the 20s and 30s. And here's Edwin Hubble looking particularly dapper. So what he did is, this was at a time, by the way, when we didn't know what galaxies were. I mean, look out at the sky. Is it super obvious what galaxies are? We have no depth perception on the sky, right? So if you are good enough with a telescope to point it at something like Andromeda and see a spiral, how can you tell them that spiral is not just a cloud that's nearby us, right? So Edwin Hubble needed to figure out, first off, the distances to things. And what was gradually figured out in the early 1900s was that all the stars that we can see were relatively close by, within a certain distance. They were all part of the Milky Way. But then when we looked at those spiral nebula, it turned out they were much farther than all the stars that we could see. They were separate from our galaxy. They must be other galaxies. And maybe we live in a galaxy. Maybe the Milky Way is a galaxy and those other spirals are different galaxies. Oh, and now we started putting it together, right? So Hubble wanted to know the distance to the other galaxies. In order to make all that happen, that's what had to be figured out. And what happened is he realized that when he looked at the most distant galaxies and he measured their Doppler shift, they were all moving away from us. All of them. All distant galaxies are moving away from us. And that's a heck of an observation. If everything is moving away from us, doesn't that mean we're the center? So let's think about this here. So what he actually did is he measured distance. So here's a graph that, based on Hubble's data from the 1929, what he did is he measured distance in a unit called megaparsecs. And then he measured speed away from us, measured using the Doppler effect. Recessional velocity is the speed that something is receding from us, moving away from us. Recessional velocity in kilometers per second. And what he found is an increasing line. As distance increases from us, right, the farther galaxies have higher speeds. The farther galaxies are moving faster away from us. This was a shock. What he expected to find is no pattern at all, is that some galaxies are coming closer, some galaxies are moving away, and it's a bit like particles in a gas, just random motion. But that's not what he found. What he found is that the farther the galaxy, the faster away from us it's moving. And it's a direct linear relationship. That means if something is twice as far, it's twice as fast. 3 times as far, 3 times as fast. All right? The farther a galaxy is, the faster it's moving away from us. So the way he did this was by looking at the Doppler effect on distant galaxies. We know where hydrogen lines normally are, and when he looked at very distant galaxies, he found that they were all redshifted. And remember, if something is not moving at all, it will have zero redshift. So when he looked at farther and farther and farther galaxies, he found more and more and more redshift. The lines were more and more and more shifted to the red. They would be quite literally, if a galaxy was twice as far, it would have double the redshift of another galaxy. Okay? So all distant galaxies had red-shifted light, and that means most galaxies moving away from us. This is true for the distant galaxies, not the nearby ones. Super nearby galaxies, this effect would be very small anyway. And if they're very close to us, then, for example, Andromeda, our next door big neighbor, which is actually bigger than us. Andromeda is close enough that it's feeling our gravity, we're feeling each other's gravity, and we are approaching each other. And in a couple billion years, we will actually collide with Andromeda. It'll be an interesting event. And but that's because they're close enough that this effect is very small. Remember, this effect gets bigger as you get to increasing distances. So it should be moving away from us, but only a little bit. But overall, it's so close that we have strong gravitational attraction, which is going to lead to a collision. All right? As you go to more and more and more and more distant galaxies, you find this much more strongly. And so all distant galaxies are moving away from us. Everything is rushing away from us on big scales. We call this Hubble's law, that the speed of the recession is proportional to the distance. So galaxies that are twice as far are twice as fast. So we can write this as an equation. Here we see velocity, recessional velocity v equals Hubble's constant, h naught, times distance. All right? And h naught is a constant that we would love to know as accurately as we can. So if you have double the distance, well, this is just a number. If you double the distance, you double the speed. All right? Hubble's constant, h naught, is normally given as about 72 kilometers per second per megaparsec. A megaparsec is a very big distance. So every megaparsec that you move away from us, the galaxies will be moving 72 kilometers per second faster. All right? So this relation can be used to determine the distance to galaxies that are very far away. And that's extremely useful because, like I said, in astronomy, it's very hard to figure out distance. But now it turns out if you can measure the Doppler effect for any distant galaxy and get its speed, now you can figure out its distance. Because there's a relation, for distant galaxies only, there's a relation between speed and distance. The farther they are, the faster they are. So if you know how fast they're moving, you know how far they are. So that's Hubble's law. Okay, again, recessional velocity equals Hubble's constant times distance. And h naught, Hubble's constant in particular, is very useful. It has units of per second, right, or per time. It's got weird units, kilometers per second per megaparsec, but kilometers is distance and megaparsec is distance. So kilometers per second per megaparsec distance sort of cancels out in a way, and it ends up giving you time, right? So Hubble's constant tells us the rate at which the universe is expanding. So let's look at a numerical example. Let's say we know the speed and we want to figure out the distance. Speed equals Hubble's constant times distance. If you divide both sides by Hubble's constant, you can say distance equals speed divided by Hubble's constant. So let's say we use the Doppler effect to figure out the speed of a galaxy moving away from us, a very distant galaxy moving away from us at 13,000 kilometers per second. So Hubble's constant, I already told you, is 72 kilometers per second per megaparsec. 13,000 kilometers per second divided by 72 kilometers per second per megaparsec ends up giving us 181 megaparsec. A megaparsec, like I said before, is a very big unit. Mega is the way you write million. So like a megabyte is a million bytes. A megaparsec is a million parsecs. And I did tell you what a parsec is before. It's like 3.26 light years. So you can convert this. 181 megaparsecs is about 600 million light years away, which is pretty far. All right, pretty far, 600 million light years away. So a mega, again, is a million, and a parsec is about 3.26 light years. So it's a little bit bigger than, well, it's a few light years. Right? And again, we'll talk a little bit more about this. There's a reason why astronomers use parsec, and it has to do with history. It's kind of the same reason that certain countries are stuck on inches, right? History. It's a stupid unit, but some people still use it. So anyway, you saw Hubble's data. Here is some more modern data. And indeed, there is a very linear relationship here. As distance increases, velocity increases. You have a flat increasing line, and it is a slope of 2. So it doubles. So as you go, or it's straight linear anyway. The slope is actually Hubble's constant, but so I was wrong about that. But the slope is Hubble's constant. The important point is it's a flat line, which means it's linear. So if you go twice as far, that's what I meant. If you go twice as far, then you get something twice as fast. All right. Or if you go 3 times as far, you get 3 times as fast. 10 times as far, 10 times as fast. All right. That's what you get with a line. The slope of the line is Hubble's constant. So what this tells us is that the universe is expanding. It seems weird to say that everything is moving away from us, right? Again, if you picture that, everything moving away from you, it sure seems like we're the center of things. Because imagine you're at a party or something and everyone is moving away from you. Well, then you're at the center of probably maybe a smell. I don't know what you did, what you said, but everyone's moving away from you. You're the center of an increasingly empty region. But that's not quite right. We're not the center of things. And in particular, isn't it weird that the farther ones are moving faster? If you did something horribly rude at a party, wouldn't it be the closer people to you who move away faster? Right? So it's different than what you might think. So Hubble's observation that everything is moving away from us led to the idea that the universe is expanding. And it's actually the space between galaxies that's increasing, right? But it's important to remember, nothing is at the center. There is no center. This is going to be true if we were in any galaxy. We would see the same thing. The universe is expanding. One problem that I immediately know is happening in your head is you are picturing something with an edge expanding. Stop it. Okay? There is no edge. It is infinite, and it is expanding. It doesn't have to expand into anything because it's infinite. All that's happening is the space between things is growing. There is no edge. So stop picturing an edge and like a solid object just growing. That's part of the problem, right? Is here you see a solid object that looks like it has an edge and it's just expanding into something, right? But that's not quite right. And so we got to sort of digest this and figure out what this really means. So here we see a chunk of the universe. Again, you got to picture infinity. So good luck with that. Infinity is hard for a brain to picture. But here we see a chunk of the universe, and the galaxies are slowly spreading apart. They are spreading apart from each other. Any individual galaxy will become more and more isolated over time as the space between them grows. So on large scales only, galaxies are moving apart, and the speed at which we see them moving depends on their distance. Right? It's not actually galaxies flying away from us. We did not do something rude, and now everyone is getting the hell away from us. Rather, it is the space itself that is expanding. And like a conveyor belt, it's carrying the galaxies away from us. So the galaxies themselves, by the way, are not growing. If you are standing on a conveyor belt and the conveyor belt carries you away from someone else, you don't get stretched. The galaxies are not expanding because they're held together by their own gravity. It's the same reason why Andromeda is not being carried away from us. Andromeda is close enough that gravity is pulling us together, right? Galaxies are held together by their own gravity. They are not expanding. But on big scales, really separate scales, you can see this happening. So how do we think about this? Here's an analogy. Picture the universe as a piece of raisin bread. All right? The universe is raisin bread. Now, the problem is, right away, every analogy has problems, is limited. Because we're not talking about the truth. We're talking about an analogy. The problem with this analogy is this raisin bread has an edge, and it has a center. So what I kind of need you to do, I suppose, is picture infinite raisin bread. And again, good luck with that. But that's what you would need to do if you really want to extend this analogy. Anyway, the point is, take a piece of raisin bread. The bread is space, and the raisins are the galaxies embedded in space. Take that raisin bread that you've just made and put it in the oven and bake it. And as it bakes, it will rise. The bread will expand, carrying the raisins apart from each other. If you look at this raisin, right, this is us. If you look at this raisin, it initially has raisins that are a certain distance away from it. And then over time, raisins are moving away. And this raisin will say, oh, why is everyone leaving me? Right? What have I done? Everyone is moving away from me. But is that only true of this raisin? No, it's true of any raisin that you could look at. This raisin will see galaxies or other raisins at different distances, and over time they will move away from it. So any galaxy is seeing the same thing, expansion. And it's because it's not that they're moving away from us. It's that every galaxy is moving away from every other galaxy. Everything is becoming more isolated with time as the space between things expands. In fact, if you look really closely, you can see that these raisins, which are relatively close, the distance hasn't changed that much. But the distance here has changed much more. The farther the galaxy, right? The farther the galaxy, the faster away it's moving. In the same time, this one has moved a lot farther. Why? Because there's more bread between us and it. And as the bread rises, it gets carried much further away. So the farther the galaxy, the faster away from us it'll be moving. That's Hubble's law. Hubble's law is actually accurate in raisin bread. So it's not that complicated after all. It might seem a little weird to you. You don't live in raisin bread, so maybe this seems foreign, but it's not actually complicated. Hubble's law applies to raisin bread. Here's another analogy. Take a balloon, all right? A balloon. And because, again, part of the problem with the previous analogy is that this is limited in extent, right? There's an edge. Now, pretend that our universe is the skin of a balloon, just the skin, all right? This is an analogy where our universe is two-dimensional. It is the skin of a balloon, but it wraps around. So this is an interesting universe where you could travel along in the universe, again, only on the rubber. We're not getting out of the universe and leaving the rubber. We're staying on the rubber. And if you stay on the rubber, you will walk around for as long as you like. You could even walk all the way around. You will never find an edge. You will never find a center. Everywhere on the rubber is the same as everywhere else. This is what we call a closed universe. You can actually walk around it. It's not infinite, right? There's a limited amount of rubber, but there's still no edge and there's still no center. So this is actually a very different analogy that works maybe better, but it is only two-dimensional. You can go left, you can go right, you can go, this way or this way on the balloon, but you cannot go vertically out from the rubber, right? You can't leave the rubber, so it's only two-dimensional, whereas the bread is three-dimensional. In the bread, you could go, in and out of the bread, you can go up and down on the bread, you can go side to side in the bread, but three-dimensional, but it's limited. Here, it's not limited, but there's only two dimensions, all right? Anyway, so in this analogy, imagine that it is expanding, just like our universe actually is, and as the balloon inflates, what happens to the skin, what happens to the actual universe is stretching. The rubber stretches, and every galaxy, here it's little dots taped on. The dots don't change size because they're taped on, but the distance between each dot increases over time. Everything is moving away from everything else. All right. Now, what's interesting as well is that because this is happening, the light that's coming to us from distant galaxies also gets stretched. That's actually the cause of the redshift. Like I said, it's not actually that distant galaxies are moving away from us at some high speed. They're being carried along. They sent out their light, potentially millions or billions of years ago. So why does that light look redshifted? It's actually because as the universe expands, the light gets stretched. And when you stretch light, it becomes redder or redshifted. So it's actually, the truth is, it's actually not quite a Doppler effect. that we're seeing from distant galaxies is what's called cosmological redshift. But it's fine enough to continue saying galaxies are moving away from us. The farther they are, the faster they are, and we can see that as a Doppler redshift. All right, it's equivalent. It doesn't really make a difference. So nonetheless, the recession of galaxies, the fact that they're moving away from us, is not caused because the galaxies are actually flying through space. As you can see, this galaxy, for example, is taped to those grid lines. And over time, it's not moving across grid lines. It's stuck to those grid lines. It's not moving through space much at all. It will be a little bit, but it's not moving much. It's stuck to those grid lines. What's happening is space itself is expanding and carrying these things apart. All right? It's the expansion of space itself. So as space expands, it stretches. There's a good video on this if you look it up on YouTube called the Everywhere Stretch, which probably is a better name than Big Bang, the Everywhere Stretch, because everywhere in space is stretching. All right? And the more space there is between two different galaxies, the faster the stretch will appear to be happening. So the universe's expansion is stretching the light. That makes distant galaxies look redshifted. And they are redshifted. The light that we get from them is more red. All right? So what happens if you hit rewind on this expansion that we can still see happening? What happens as you hit rewind is everything comes back together. And at a certain point, those galaxies all start to basically overlap until the point where on the balloon or in the raisin bread, the raisins basically touching, and you reach a point at which things become almost infinitely dense. Again, don't picture edges closing in on themselves. We're picturing infinite bread, and all the raisins are becoming infinitely dense as we run back towards the Big Bang. Right? If the universe is expanding, then at some earlier time, the universe must have been, in a way, smaller, denser, really. But everything that we could see, everything that we can see right now, out to the farthest reaches that we can see, would have been packed into a very tiny volume at the time. Even then, the universe would have been infinite in extent, but everything would have been very close together. All right? So as we go back and back and back, things get denser and denser and denser until at some point, the universe becomes almost infinitely dense. And everything that we can see now was compacted into a tiny, tiny point. Again, there'd be more outside that point. The universe was infinite. All right? And it still is. But when everything gets almost infinitely dense, that marks the point where we call the Big Bang, when everything sort of started to expand outwards, the start of the universe. And we don't really understand that time very well. We do have incredibly dense information on the Big Bang. Okay, we understand a lot about it, so do not get carried away. This is not a thing that we don't understand. If you want to take a follow-up course to this, called Advanced Topics in Astronomy. I teach that as well, and I will teach you quite a lot about what was going on in terms of the physics right after the Big Bang. And we understand a lot about it. You might not. That doesn't mean we don't. Okay, it is complicated. It is a strange time. But the problem we come to is that at a certain point, things become so extreme. When you get to really infinite density, you're dividing by zero. And so the calculators start to fail. And we start to reach limits of quantum mechanics, and we have trouble understanding what was going on. But nonetheless, it's very well understood, okay, for the most part. There are questions. That doesn't mean it's not well understood. So that was the time of the Big Bang, or the Everywhere Stretch. And again, Google that, okay, Everywhere Stretch. Check it out. It's a good video. So the simplest is that when the universe was really dense, space was very hot and curved, and it started to expand outwards. An initial push that we call the Big Bang. It's a terrible name because what you picture, I presume, is an explosion of things out into space. And that's a mistake. It's not an explosion of things out into space. It's actually the expansion of space itself, carrying things apart. All right, so the Big Bang, and it wasn't big, it was everywhere. So it's an infinite stretch. Right, it's an everywhere stretch. But anyway, Big Bang is what it's called. The truth is, the name was actually developed as a joke. One of the initial scientists proposed this name as a joke. He said, "This idea is stupid. Let's call it this Big Bang you're talking about. Anyway, it's a stupid nickname, but it's stuck, and now we're stuck with it. It's not an explosion. It's the initial expansion of the universe. So now let's think about our view. As we look farther and farther and farther away, we look farther and farther back in time. If we look very far away, billions of years into the past, we see galaxies as they were billions of years into the past. But it turns out the Big Bang was about 13.8 billion years ago. So what happens once you start looking 10 billion, 11 billion light years away? You start to see galaxies as they were right after the Big Bang. And there is a time, as you look further and further into the past, the deep fields don't actually look all that deep. If you look at the ultra deep fields, you see galaxies when they were very young, the very first galaxies. If you look even farther than that, it becomes hard to see anything because there weren't even many stars at that time. We enter what's called the Dark Ages, where nothing was really happening. And so as you look to more than 13 billion light years away, there's almost nothing to see. Plus, it's incredibly far, so good luck seeing anything. But if you look really close, 13.7 or more billion light years away, you're seeing light from right after the Big Bang. We can see that. We can see the light from right after the Big Bang. It's called the cosmic microwave background radiation. It's the background because it's in every direction. When you look 13.8-ish billion light years away, you see that radiation. It's microwave light, and it's the leftover heat from the Big Bang itself. And you can't see any farther than that because the universe didn't exist before 13.8 billion years ago. So, how do we know the age of the universe? It's simple. Take Hubble's constant and just do 1 divided by Hubble's constant, and that gives you the age of the universe. That's called Hubble time. All right. This is why a lot of scientists study Hubble's constant to get as accurate a measure as we can, because the current measure that we get is not super accurate. It's 7 to 15 billion years old. But the best studies that we have tell us the Big Bang was about 13.8 billion years ago. And that's in that range. So the universe is about 13.8 billion years old. What will happen in the future? Well, the universe could just keep expanding forever. That's what we call an open universe. It's just going to keep opening out. And that is what we think will happen. Or it could collapse. Eventually, gravity could grab hold of things, and if gravity is strong enough, then it could cause everything to recollapse in a closed universe. And that's pretty interesting to picture, but unfortunately, we don't think that's going to happen. Right? So if the only thing that mattered was was gravity, if the only thing that mattered was gravity, then it would simply depend on how much stuff is in the universe. Is there enough gravity to eventually recollapse things or not? If there's not a lot of gravity, the universe would just expand forever. If there is a lot of gravity of stuff in the universe, then that gravity would pull things back together eventually, and the expansion would stop and recollapse. And so it depends on the density of stuff in the universe. All right. So density is how much stuff is there in a given amount of space. So here's the idea overall: is the universe is expanding right now. Right. Right now the universe is expanding. If there's enough stuff, gravity would make that slow down, and then eventually reverse and recollapse into what we call a big crunch, which would be dramatic, but we don't think that's going to happen. As it happens, gravity is pretty strong, but it's not going to be strong enough. The universe will continue to expand and expand and expand forever. In particular, the reason why we think this is because we have discovered, in the last decades, we have discovered a mystery that we call dark energy. And dark energy is a force that opposes gravity, and we don't understand it at all. And it is one of the biggest mysteries in all of science, is it does seem like it's not just gravity that's out there that's governing what's going to happen to our universe. It seems like there's something else that is helping to expand. And so the Big Bang caused everything to move apart, and dark energy is actually sort of encouraging that. Gravity would be slowing it down. Dark energy is doing the opposite. And dark energy is helping the universe to continuously expand. And it looks like it'll expand forever until eventually the universe cools off. Everything separates to the point of seeing nothing. Everything is completely isolated, cools off to 0 degrees, and we reach what we call the heat death. of the universe, which is pretty depressing. And that's where we're going to leave it. So we've been talking about a lot today. We talked about light and how useful it is, and how something like the Doppler effect eventually taught us that the universe is expanding and gave rise to the idea of the Big Bang itself. Along the way, we talked a little bit about galaxies, but galaxies are very important and very interesting and very beautiful. So next class, we're going to take a closer look at galaxies. What are they like? How do they form? What's our Milky Way like? And all sorts of cool stuff to do with galaxies. So we'll be back for that later, but first what we're going to do, as always, and hopefully if you're watching this right on time, then what we'll do next now is our after class homework and the quiz take up of today's material. All right, so next class, galaxies.